Hello, this is Byron. Sorry there was such a long delay since the last video. Last time we talked about the life cycle of low mass stars. So this time we're going to talk about the life cycle of intermediate mass stars. Let's jump right into it. Today we are going to be talking about mostly B-type stars. B-type stars have an astonishing range of masses, from around 2 solar masses to over 10 solar masses. And we are going to be talking about 2.5 to 10 solar masses, so it's just going to be B-type stars today. This image is an example of a B-type star. In fact, it is alkyd in a simulator, and someone has taken a screenshot inside the simulator. Unfortunately, I couldn't find any images of alkyd from a telescope or anything. So B-type stars like alkyd, when they run out of hydrogen in their cores, they have to come from, just a moment, laser pointer. So B is around here-ish. So we go from here and they go almost horizontally. This is the this is the Hertzfeld diagram for Hipparchus, for the Hipparchus mission. So here they go almost horizontally, and Hertzsprung saw all this and realized that a gap between here and here. Since there are relatively less stars, and from the solar mass stars to the red giant and to the foot of the red giant branch here. So it turns out that in these stars, once hydrogen shell fusion begins, they quite quickly become giants. And so this, even though the line for giants goes through this place, they are evolutionary subgiants, although they are usually classified as giants because they haven't become giants yet. You see, as this has a lower temperature and the same luminosity, and therefore it must be increasing in diameter from here to here. So these are dwarf stars and these are giant stars, so they are evolutionary subgiants. So then they go to the foot of the red giant branch, and from here on it seems like it would go the same way as it did for lower mass stars. But here quantum mechanics comes into play, because this thing I forgot to explain about degeneracy. It's a thing in quantum mechanics where if there are two particles, say two electrons, which are of the same type, and they are in the almost in the same place, quantum mechanics doesn't allow that. So there is a force known as quantum degeneracy pressure pushing them apart. And for smaller stars, the helium core becomes degenerate, and this means that they go until the tip of the red giant branch. Because again, due to quantum mechanics, if you have degenerate cores and you apply it under pressure and it becomes smaller, it does not heat up. Instead, it stays the same temperature. Meanwhile, for a non-degenerate core, it heats up. So to fuse helium, it has to wait until the hydrogen shell around around the core heats it up to the point where helium fusion can begin. So it goes up to the tip of the red giant branch. While now the core is non-degenerate, so it gets hotter quicker and then comes back earlier. For this, I just want a different diagram which shows what happens to a 5 solar mass star. So here it doesn't go until the tip of the red giant branch, which is somewhere here. Instead, it goes here and starts helium fusion. And another difference is now it becomes hotter and bluer because of the helium fusion, and it's slightly different from the lower mass stars again. And it doesn't really mean a blue loop. Here it doesn't go all the way to blue, only very light blue. And this part and all is not blue at all. This is white and yellow. So generally in astronomy, when people say blue, they mean bluer. Like blue, the A-type stars are bluer than F-type stars. And so what happens now is it becomes a bit more luminous and then comes back, and then it ends helium core fusion because all the helium is exhausted in the core, and it becomes helium shell fusion and goes through the same process of asymptotic giant branch. And I also have another example to share. There is a Canopus, which is a very famous star. It is the second brightest star in the night sky. Is currently on a blue loop, which is why it's much bluer and brighter. It is actually a bright giant according to the Hertzsprung diagram, which means it's higher than a normal giant because it's actually around 8 solar masses. So you can see Canopus is around here, and it is classified as a bright giant. But you can see from here that it's because when it's coming back in the blue loop, its luminosity is highest at this point, and these might get misclassified as bright giants. Unfortunately, I could not find any examples for an intermediate mass star which is on the red giant branch or asymptotic giant branch. Afterwards, it's pretty much the same. The same carbon, oxygen, white dwarf, and a planetary nebula. That's all for today. Next time we'll be covering high mass stars, which are much more explosive than either low mass stars or intermediate mass stars.